We are back with Ampere's laws. Okay, so we just finished up talking about Biot-Savart, where we have a long straight wire or a wire loop from these two equations. These amazing equations here. And we're going to take a look at some examples here, okay? Our first example we're going to look at has to deal with some looping to an extent. What we have here is we have kind of a wire frame that's been bent around and a current's running through it. Don't ask how the current got there, children, okay? It's just there. And when we look at this, we are trying to figure out what is the magnitude, so what's the size, and the direction of the magnetic field at point C down here. So that's what we're trying to do here. So to do this, we actually need to figure out what the B field's direction is and strength is from points A, so this curve underneath, B, the curve over the top, and then each of these two little straight lines here, like that, okay? Now the way we're going to go about doing this is we're going to first start with the straight lines at the side. And the reason why we're going to start with the straight lines at the side is one of mega convenience. Whenever we traditionally look at the Biot-Savart laws, if this is our current carrying wire, the radial distance is measured away from it, like this. If we are on the wire, like that, or like in front or behind it, we're not going to generate or have any B field there. You're like dividing by zero, which breaks a lot of mathematics, so to speak. But physically, there is no B field there. So if we take a look at these lines here, these lines are directly in line with C. So these two lines here are going to provide zero B field, okay? We get zero out of those. Nada, zilch, nothing. So the only things we actually have to care about is we have to care about the B field from line A here. We care about that. And we care about the B field from line B, the line going over the top in this poorly drawn arc by yours truly. Okay? That's all we care about. Now, in order to get these, we need to use the equation that the B field here is equal to mu naught I phi over 4 pi r. And we'll have to do this for both of them. Now, the great thing about this is angles are not dependent on distance. So if we take a look at this here, our phi is 5/8 pi radians. And this is super duper important. Your angles must be in radians here. Radians are the kind of ratios between radius and amount of angle that you've encompassed on a circle. It is like the only kind of true physical property, so to speak, that we have. Degrees are just a made-up thing to make math work. We care about radians here. So this is our phi value. Our two R values in this case are, for this problem, there's no real numbers, so it's just going to be A for A, and it's just going to be B for B. So if we take a look at what these would be, we're just going to have mu naught, the current of 2.5 amps, which is kind of constant for everything. So there's our current. Phi, which is 5/8 pi. And I guess we'll just put in the current. Might as well just put in the current. So there's our 2.5 divided by 4 pi a. And if we go ahead and do the same thing for B, it's going to be the same equation, mu naught times 2.5, those are our currents, times the same angle, 5/8 pi radian, divided by 4 pi b. Now, in this case, if we were to add these together, if we take the B field from A and we add it to the B field from B, we're going to get our total B field here, our net B field. And this is something we need to be careful about. Right hand rule time. If we take our thumb and point it along the current carrying wire, we are going to see that for wire A along the bottom here, underneath wire A as we see it, that B field is going to be pointing into the board. Okay? If we do the same thing for wire B going across the top and we roll our fingers around, we're going to see that wire B is actually coming out of the board. these are in opposite directions, okay? So we need to pick one of them to be positive and one of them to be negative. I always like picking going into the board being positive, and that means coming out of the board is negative. But what this means is I don't have the B field of wire segment A plus the B field of B. Since I'm adding that negative quantity, it's really like a subtraction problem. So if we wanted to write this out, what we're going to have in the end is, notice that I can factor out mu naught, the 2.5, the 4 pi, and then the 5/8 pi. So what I'm really going to have in the end is mu naught times 2.5 times 5/8 pi divided by 4 pi, and I'm going to have the quantity 1 over A minus 1 over B. Okay? And if you had your B as being positive and A as being negative, it'd be 1 over B minus 1 over A. Okay? But this is our net B field here. Yes, if you wanted to, you could say, oh, look at these pi's, they go away. And, look, I can take the 4 and put it with the 8, so it's like 5/32, and then that, whatever. Okay? The big thing here is that you need to recognize that the direction matters. Okay? The big thing is that direction matters here, and we are using the Biot-Savart equation that it is mu naught I phi over 4 pi r. Okay, with the direction that matters. So that's our first little example there. For our second example, let's roll it down a little bit. We have an infinitely long wire, and then this infinitely long wire is bent into a bit of a circular loop right here. Okay. Now, we would once again like to know what is the B field strength at the center of that loop at point C. So how do we go about doing this? Well, we've actually got 3 segments here. Our first segment in blue here is a long, infinitely straight wire. So we can use this initial segment as just being mu naught I over 2 pi r. Then we have a loop here. Now, if that's half of a circle, we know a circle is 2 pi radians, so half a circle is just going to be pi, but that means the B field here is going to be mu naught I times phi, which will be pi in this case, divided by 4 pi r. And then our last term that we're going to have here as we come out of this is we're going to have another B field, which is mu naught I over 2 pi r. And we need to add all of these together in order to get this final quantity. Okay? Now, just like in the last problem, we need to be careful about directions. And if we actually run through this everywhere, so for our blue top one, it's going to be coming out of the page at this point. If we look at our pink as we wrap it around, it's also going to be coming out at this point. And if we look at the green, as we kind of like retwist it, we can either like break our arm like that, or we can just kind of flip our hand and do this with our right hand. We'll see that the green is also coming out on the inside. So all B fields point out of the page here, so we can add them all together. They're just, none of them are going to fight against each other. We've got a nice setup there. So we just need to find all these values, and then we can just churn them all together. So in short, what this will look like for our net B field is, and we'll do each of these one at a time, it's going to be mu naught times the current, which is 7.06 amps, divided by 2 pi times the R value, which in this problem is 3.4 times 10 to the minus 3. So 3.4 times 10 to the minus 3, that's a 3. And then we're going to add that to, well, I guess I should have done that in blue. Here, I'll go back. I'll rewrite this. I'll rewrite this so all the colors match. Matching colors is important. So like I said, mu naught times 7.06 divided by 2 pi, and then 3.4 times 10 to the minus 3. And remember, that mu naught is just a constant. That mu naught is just a constant, 1.26 times 10 to the minus 6th. So if you need that, mu naught is 1.26 times 10 to the minus 6th. But then we'll start adding things up. So we'll add this to the curved loop here, which is mu naught, once again, times the current, 7.06, times pi, because we're going through half of a circle, divided by 4 pi, and then this is, once again, that R value is going to be the same. It's going to be the 3.4 times 10 to the minus 3. And then we need to add that to the last piece, so plus And actually, this is kind of fascinating. You could add this last piece here, but you're going to see that it looks exactly like the blue piece that came before it. So you could, add it right here, or what you could just do is you could just run back to the beginning and multiply this by 2. And I think that's actually a little bit easier to do that, okay? So this last piece here, it was just adding the same thing. It acted in the same direction, so they were helping. So we just said, hey, look, let's just multiply by 2 out here. And this actually makes things nice because 2 over 2 is a nothing. So we were able to kind of simplify this out. But if you didn't want to, if you wanted to just leave it all so that we know what we're talking about, that would be it. You'd crunch all these numbers together, and you'd get your final answer. And do I know what that is? Of course I don't, but I know it's in Tesla, and I know if I shove all those numbers in a computer and I do it very carefully, I'll get something there. But remember, numbers are the enemy, and they're the work of the devil. So this right here will give us enough information about what's going on. It's important that we recognize which of Biot-Savart's equations to use, either mu naught I over 2 pi r or mu naught I phi over 4 pi r, and then once again, look at your directions with your right hand rule to figure out what's going on there. Okay? So with that, these little examples here are finished. Adios, and you take it easy.